In this video, we discuss basic properties of groups. So what are some consequences of the definition of a group? Okay, so first let's recall the definition of group. So we're going to start with a non-empty set G equipped with a binary operation, so a function from G cross G to G. And this set will be called a group if the following axioms hold. So first we have closure, and again, this is implicit in our definition, but namely that if A and B are in G, then combining A and B with our operation lands us inside of G. We have associativity, so that A dot B dot C is the same as A dot B dot C for all A, B, and C in my group. We have the existence of an identity element, so we'll call this E, such that A dot E is equal to A, and E dot A is equal to A. So this is kind of our neutral element. And then finally, we have inverses. So if A is in my group, then there exists some element B in my group such that A dot B is the identity and B dot A is the identity. So I can invert any element and get back to the identity. And then finally, a group G is called abelian if it has the commutativity property, namely that A dot B is always equal to B dot A for every element of my group. Okay, so what are some of the consequences of this definition? Let's find out. Okay, so the first consequence of our group axioms is that the identity element E is actually unique. So how does this go? Well, it's a typical uniqueness proof. We're going to suppose that we have two elements, E1 and E2, that both play the role of the identity. So we're going to suppose that E1 times A is equal to A, and A times E1 is equal to A for all A, and E2 times A is equal to A, and A times E2 is equal to A. And we're going to assume that this is true for all A and G. Well, let's think about how this goes. Then, if I think about this, E1 has to equal E2 times E1, right? Why is that the case? Well, that's the case because I'm using the following property. I'm using property, this guy, I'll color it in orange, with A equal to E1. All right, so I'm using this property here. And I'm just writing it backwards. I'm writing it as A is equal to E2A. And then finally, I might notice that E2 times E1, well, E1 times anything gives back that element. So E2 times E1 should be E2. So now what am I doing? I'm using this property right here with A equal to E2. All right, so this equality follows from the orange, or from the green rather, and this equality follows from the orange. So I could say hence E1 is equal to E2. Okay, so that's our first consequence. The identity element is unique. Okay, so our next consequence is that inverses are unique. So how do we prove that? So I'll suppose A is in G, and I'll suppose that A has two inverses. Let's call them B1 and B2. So I have A times B1 is E, B1 times A is E, and I also have A times B2 is E, and B2 times A is equal to E. Okay, so where does that lead me? Well, let's think about this. So then I have the following. I have that B1, I can write this as E times B1. Well, what is E equal to? I know that E can be rewritten as B2A times B1. Okay, I know I have associativity, so now I can move my parentheses. I could write this as B2 times AB1. And I know that AB1 is equal to E, so this is B2 times E, which leaves me with B2. So hence, I see that B1 is equal to B2. Okay, so this is kind of nice because now, so I'll put a little box here to end the proof, but now we can just write A inverse for the inverse of A, since we proved that there's only one inverse for any element. So we can call this element now A inverse. Okay, and a third property now is what's called the cancellation law. So if A, B, and C are elements of my group, and AB is equal to AC, or BA is equal to CA, then I can just cancel out the A's. So I have AB equal to AC implies B equals C, and BA equal to CA implies that B equals C. So I can cancel out the A's. So how does the proof of this go? Well, let's think about this. If I have AB is equal to AC, well, if I multiply by A inverse on both sides, I'll get A inverse times AB is equal to A inverse times AC. And now I could use associativity to slide those parentheses over. So this is going to be A inverse A times B is equal to A inverse A times C. And where does that get me? Well, A inverse A is equal to E, so I have EB, and A inverse A is equal to E, so I have EC. which implies that B equal to C. Okay, so that's one direction. And I'm going to just say that BA equal to CA implies that B equal to C is similar. The idea is we now multiply by A inverse on the right side. Okay, so that finishes that consequence. Okay, so here are some more consequences of our definition. So we'll let G be a group, and I'll let A and B be elements of G. Then a natural question to ask is, well, what is the inverse of the new element AB? So what's the inverse of AB? It turns out that the inverse of this element AB is just B inverse times A inverse. You might also ask, what's the inverse of A inverse? It turns out that the inverse of A inverse is just A. So we're going to prove this. So let's start with a proof of 1. So one thing that I know, by definition of inverse, I know that AB times the inverse of AB should equal E, and the inverse of AB times AB should equal E. Okay, right now we don't know what the inverse of AB is. It's just some other element of our group. Okay, what else do we know? We also have the following. We also have, if I take AB times B inverse A inverse, well, what does this equal? If I move my parentheses around, I'm really just looking at AB, B inverse, A inverse. This is going to be A times E times A inverse, which is just A times A inverse, which is equal to E, right? And there's some parentheses shuffling that I'm avoiding here just for the sake of avoiding clutter. So I'm just kind of ignoring the movement of the parentheses, but with associativity, everything works out here. So I notice that AB times this new element here gives me E, and then I'll do it in the other order as well. If I take B inverse A inverse times AB, again, avoiding all this parentheses shuffling, I'll just write the following. This is going to equal B inverse E times B, which is B inverse B, which is equal to E. So I see that this element here times AB also gets me E. Well, what do I know? I've just shown that this new element, B inverse A inverse, is also the inverse of AB. So I could say by uniqueness of inverses, right, AB is only allowed to have one inverse. So by uniqueness of inverses, it must be the case that the inverse of AB is equal to B inverse times A inverse. So that proves 1. So I'm using the fact that I just proved, I'm using consequence 2, the fact that inverses are unique. Therefore, these two have to be equal. The proof of 2 is actually quite similar. So what I know is that if I take A inverse times this element A inverse inverse, I should get E. And if I take A inverse inverse, whatever this element is, times A inverse, I should get E back, right? That's just by definition of inverse. The other thing I know is that A inverse times A is equal to E. And I also know that A times A inverse is equal to E. Well, I know that A inverse has to have a unique inverse. So I can say by uniqueness of inverses, again, by uniqueness of inverses, I'm forced to conclude that A is equal to A inverse inverse, that A is the same as the inverse of A inverse. Okay, so that proves my theorem here. So now that we've established some basic facts, we can establish some notation, which in context will now make sense. So I'll let n be a positive integer. And what I'm going to do is I'm going to write a to the n, and I'm going to interpret this as just a times da 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 times a, where I just have n copies of a. So it's just n copies of a being multiplied. If I encounter an a to the 0, I'll just interpret that as e, my identity element. And if I encounter an a to the minus n, all I mean is it's just n copies of a inverse multiplied by one another. And these have some pretty straightforward properties, namely that a to the m times a to the n is a to the m plus n for all integers m and n. And also a to the m to the n is equal to a to the mn for all integers m and n. Okay, so this is our notation, and you might ask, well, how does this notation carry over if I have a group under addition? So if G is a group under addition, we actually use the following notation. We use 0 for E, right? Typically zeros are additive identity in any group under addition. So we'll just call that element 0. And we'll use minus A for A inverse. So we'll just call that element negative A. And we write the following. Instead of A to the n, we write NA. So NA is just A plus A where I have n copies of A. If I encounter 0 times A, so this is our analog of A to the 0, I'm going to call that 0. That's my identity. And if I encounter negative n times A, that's just going to be negative A plus dot plus negative A, where I have n copies of negative A. And then finally, we have analogous properties, namely that MA plus NA is M plus NA, and N times MA is MN times A. Okay, so this is going to be the notation we established. So on the left-hand side, we have the multiplicative notation. On the right-hand side, we have the additive notation. Okay, so we're ready to discuss the notion of order of an element in a group. So I'll say let G be a group and let A be an element of G. We'll say that A has finite order if there is a positive integer k such that A to the k is equal to E. So if there is some power of A, some positive power of A, that gives me back my identity element, we'll say that A has finite order. The order of A is going to be the smallest positive integer k, such that A to the k is equal to E. So the smallest positive power of A that gives me back E is going to be called the order of A. And we'll use this notation, we'll use this absolute value notation, and we'll say the order of A is equal to k in this case. Okay. And if no such k exists, so if there is no positive power of A that gives me back the identity, we'll say that A has infinite order. Okay, so let's look at a few examples. So the first example we can look at is the group U of Z10. So this is the group of units of the ring Z mod 10. And remember, these are the elements of Z mod 10 that are relatively prime to 10. So 1, 3, 7, and 9. And this is a group under multiplication. So let's consider the orders of some of our elements. Well, one thing I know is that the order of 1 is equal to 1, right? Because 1 to the first power is equal to 1. So I can say that the order of 1 is equal to 1. Okay, not that interesting. What about 3? Well, let's take a look. I know 3 to the 1 is 3, so that's not the identity. I know that 3 squared is 9, so that's not the identity. I know that 3 cubed is 27, but 27 mod 10 is just 7, so that's not the identity. And then I see that 3 to the 4th, this is equal to 81, which is equal to 1 mod 10. So I see from this, the smallest power of 3 that gives me back 1, my identity, is 4. So I'm going to say that the order of 3 is equal to 4. Okay, so let's repeat this for some other elements. What about 7? I'll notice that, okay, 7 to the 1 is 7. That's not the identity. 7 squared is 49. Well, 49 mod 10 is 9, so that's not the identity. I'll notice that 7 cubed will be 3. And then I'll notice that 7 to the 4th is actually equal to 1 mod 10. So I notice that the order of 7 is equal to 4. Okay, and then finally we can repeat this for 9. I notice that 9 to the 1 is 9. So that's not the identity. But I know that 9 squared is 81, and 81 mod 10 is 1. So I see that the order of 9 is equal to 2. So 9 is an element of order 2. Okay, and again, I'm just always looking for what's the smallest power of my element that gets me back to my identity. In this case, our identity is 1. So I'm asking what's the smallest power of my element that gets me back to 1. Okay, so here's another example. Here's an example of a group under addition. So our identity element here is 0. We're working with Z mod 12. And let's pick an element. Let's say we look at the element 4, right? Well, 4 is just equal to 4. If I combine 2 4s, if I do 4 plus 4, I get 8. That's not equal to 0, which is my identity. And if I do 4 plus 4 plus 4, that is going to equal 12, which is equal to 0. That's my identity. So I can see that the number of 4s I need to combine before I get the identity is 3. So the order of 4 in this group is 3. I can repeat the same process for 2. I could say, okay, 2 is equal to 2. 2 plus 2 is equal to 4. 2 plus 2 plus 2 is equal to 6. I'm still not at the identity. 2 plus 2 plus 2 plus 2, that's equal to 8. That's not the identity. 2 plus 2 plus 2 plus 2 plus 2, that's equal to 10. That's not the identity. And then finally, I can say, well, if I combine 6 2s with one another, now I get the identity. So the one thing that I notice is how many 2's do I need to combine with one another to get the identity? I have to combine 6 of them so that the order of 2 is equal to 6. One thing that might be interesting to try is to show that the order of 5, for example, is actually equal to 12. So the number of 5's I need to combine with one another before I hit 0 is actually 12. So I'm going to do 5 plus 5 plus 5 plus 5, so on and so forth until I write down 12 5's. Okay, so that's another example. This is an additive example. Okay, so our final example will be from the group S3. So I've written down a permutation of the numbers 1, 2, 3, and I'd like to figure out what is the order of this permutation? What is the order of this element? So I'm going to compose it with itself until I hit the identity element. And the thing to remember here is that the identity element that I want to hit is the element 1, 2, 3, 1, 2, 3. Right? This is the identity function. So it maps 1 to 1, 2 to 2, 3 to 3. Okay, so let's square this element. If I take 1, 2, 3, 2, 3, 1, and I square it, well, I'm taking 1, 2, 3, 2, 3, 1, and I'm composing it with itself. So this is 1, 2, 3, 2, 3, 1. Let's see what we end up with. Okay, so if I do this composition, I see that where does 1 go? 1 goes to 2, and then 2 gets mapped down to 3. So in the end, I see that 1 goes to 3. Where does 2 go? 2 goes down to 3, and then I see 3 goes down to 1. So in the end, 2 goes to 1. And then finally, where does 3 go? 3 goes to 1, and then 1 goes down to 2. So I've ended up at 2, so 3 gets mapped to 2. And I see that this is not the identity. Right? This is not the identity, so this element does not have order 2. Well, let's see if it has order 3. So if I want to do 1, 2, 3, 2, 3, 1 cubed, one clever way to do it is to do 1, 2, 3, 2, 3, 1 squared, composed with 1, 2, 3, 2, 3, 1. And I already know what 1, 2, 3, 2, 3, 1 squared is. I just did that above. This is 1, 2, 3, 3, 1, 2, composed with 1, 2, 3, 2, 3, 1. Let's see what we get when we do this. So let's fill this in. I see that 1 goes to 2, and then 2 goes down to 1. Okay, so 1 goes to 1. I see that 2 goes to 3, and then 3 goes down to 2. So in the end, 2 gets mapped to 2. And then finally, 3 goes to 1, and then 1 gets mapped down to 3. So I see that 3 goes to 3, and I get E back. So I see that the permutation 1, 2, 3, 2, 3, 1, right? So this permutation, this bijection, has order 3. Okay, so we'll move on to properties of order now. Okay, so now we'll prove the following interesting result. The idea is that if any two powers of A are equal to one another, so like a to the I is equal to a to the j, where I and j are different, we'll just assume without loss of generality that I is bigger than j, then A actually ends up having finite order. So this proof is actually kind of nice. It's nice and simple. So I can look at a to the I is equal to a to the j. And what I'm going to do is I'm going to multiply both sides by a to the minus j. So I have a to the I times a to the minus j is equal to a to the j times a to the minus j. And then if I look at this, this is really telling me that a to the I minus j is equal to a to the 0. But that tells me that a to the I minus j is equal to e. And I know that since I is bigger than j, I minus j is positive. But what does that tell me? That I found some power of a positive power of a that gives me the identity. So I can say, hence, the order of a is finite. So that finishes my proof. That's pretty elegant. This theorem actually has a contrapositive that we'll find pretty useful as well. So if I look at the contrapositive of the statement, this is going to say that if the order of a is infinite, then all powers of a are distinct, right? So the contrapositive says if not the right-hand side of the implication, then not the left-hand side of the implication, right? So if a has infinite order, then a to the I does not equal a to the j for all I and j. Okay, so this contrapositive we'll find pretty useful later on. Okay, and finally, we'll end with a few more facts about finite order elements. So the first thing we're going to do is we're going to assume that A is an element of a group G and that the order of A is n. So it means A to the n is equal to E, and n is the smallest power of A that gives us E back. The first fact we're going to show is that if A to any other power is equal to E, so if A to the k is equal to E for some k and z, then n has to divide k. We'll show that if a to the I equals a to the j, well, this is true if and only if I is congruent to j mod n. And then finally, we'll show that the order of a to the j, where j is any integer, is equal to n divided by the GCD of n and j. Okay, so let's begin our proof. So we'll prove 1 first. So I'll say, suppose that a to the k is equal to e. Well, what do I know? I know by the division algorithm, they're going to exist q and r and z, such that k can be written as nq plus r, and then specifically r is bigger than or equal to 0 and less than n. So what I'm going to do is I'm going to rewrite that power k as nq plus r. So then what do I have? I have a to the k. So this is equal to e. This is equal to a to the nq plus r. And now using the properties of my notation, this is going to be a to the n to the q times a to the r. Well, I know that the order of a is n, so I know that a to the n is e. So what I'm really looking at is e to the q times a to the r. But e to the q is e, so this is e times a to the r. And then e times a to the r is a to the r, right? So what do I have? I have that a to the r is equal to e, and r is bigger than or equal to 0 or less than n. Okay, so here's the thing. R cannot be positive, because if r is positive, I'm contradicting the fact that the order of a is equal to n. Remember, n is the smallest positive power of a. That gives me back the identity. So the only possibility here is that r is equal to 0. So this implies that r has to be 0. So in other words, this tells me that k is equal to nq. In other words, this tells me that n divides k. Okay, so that proves 1. So let's prove 2 now, and 2 is just going to be a consequence of 1. So let's look at the forward direction. So I'll say, suppose that a to the I is equal to a to the j. Well, just like before, I'm going to now multiply both sides by a to the minus j. So this gives me a to the I times a to the minus j is equal to a to the j times a to the minus j, which implies that a to the I minus j is equal to e. Well, what does that tell me? Well, I now have some power of a that equals e, so I can say by 1, I know that n has to divide I minus j, right? So remember what 1 says. 1 says that if a to some power is equal to e, then n has to divide that power. Well, I have a to the I minus j is equal to e, so n has to divide I minus j. Well, what does that tell me? Well, that's just the definition of I is congruent to j mod n. Okay, so I've proved the forward direction. So now let's go backwards. I'll say, suppose that I is congruent to j mod n. Well, what does that mean? That means that n divides I minus j, or in other words, I minus j is equal to m times n for some integer m in z. Okay, well, then I know a to the I minus j is equal to a to the mn, which is just a to the n to the m, which is e to the m, because remember the order of a is n, so anytime I encounter an a to the n, it automatically becomes an e, so this guy is equal to e. So what have I shown? Well, this implies that a to the I minus j is equal to e. Now I'm going to multiply by a to the j on both sides, so this tells me a to the I minus j times a to the j is e times a to the j. But then this tells me that a to the I is equal to a to the j. So that completes the proof of 2. I've shown that if I is congruent to j mod n, then a to the I is equal to a to the j. Okay, and finally, we're ready to prove part 3, and part 3 is a little bit tricky. So what we're going to do is we're going to establish some notation. We're going to suppose that d is the GCD of n and j, so that we can write n as n1 times d and j as j1 times d for some integers, n1 and j1. And the key thing here is going to be that if d is equal to the GCD of n and j, then the GCD of n over d and j over d is equal to 1, right? And then this gives us that n1 and j1 are relatively prime because n1 is equal to n over d and j1 is equal to j over d. So this is going to be a key fact that we need. Okay, so let's try to prove our result. So we're going to do this by a series of 2 inequalities. So the first thing to notice is that if I look at a to the j to the n over d, right? What we end up with is a to the nj over d, which is the same as a to the n to the j over d. And remember, j over d is an integer. So what does this give me? Well, this gives me that this is e to the j over d, which is equal to e. So one thing that I notice now is that the order of a to the j, the thing that I'm after, is less than or equal to n over d, right? I've shown that a to the j to the n over d gives me e. So that means that the order is capped at n over d. This is kind of like my upper bound right now. What I'd like to show next is that this inequality actually goes the other way. So let's make a little bit of space and show that the inequality goes the other way. Okay, so now that we've established this inequality and cleaned up, let's show that the inequality actually goes the other way as well, that the order of a to the j has to be bigger than or equal to n over d. Okay, so how can we do this? Well, suppose that a to the j to some power is equal to e. So let's assume k is some positive power and a to the j to that power is equal to e. Well, what does that tell me? That tells me that a to the jk is equal to e. And then by 1, I now have a to some power is e. So 1 tells me that n must divide jk. But what does that mean? That means that jk can be written as nl for some integer l. Okay, so where does that get me? This tells me that, well, I know that j can be written as j1d, so I get j1dk, and n can be written as n1d, so I get n1dl. But if I cancel out the d's, remember d is the GCD, so it's non-zero, this is going to give me j1k is equal to n1l. This tells me that n1 has to divide j1k. But I know that n1 and j1 are relatively prime, so I could say since the GCD of n1 and j1 is equal to 1, we have that n1 actually divides k. And now we assumed k was positive, so this tells me that n1 is less than or equal to k, right? So what does this tell me? Well, what is one such power k? One such power k is the order of a to the j. A to the j to its order gives us the identity. And what is n1? n1 is n over d. So I've shown the other inequality. I've shown that n over d is less than or equal to the order of a to the j. So this proves my result. I combine this inequality with the inequality that I just showed earlier up here, and I show that these two are actually equal.